Howdy, howdy, this is Mr. Potter. In today's lesson, we're going to be talking about derivatives of inverse functions, and in particular, we're going to talk about the three trigonometric inverse functions. But the process that we're going to be using here, which incorporates what we've already learned about the chain rule and what we've learned about implicit differentiation, are going to allow us to work with all inverse functions that we come across that are differentiable. And one of the properties that we will find out as we go along is that if f is differentiable on some interval, that's going to tell us that f inverse is also differentiable on a comparable interval. So let's say that I'm dealing with y equals f inverse of x. What this actually means is that if I was to evaluate the function of both sides, I would end up with f of y equals f of f inverse of x. And due to the nature of inverses, I would have that f of y equals x. And so if I wanted to try and work with the derivative, I would take a look at this expression by doing implicit differentiation. So I'm going to take the derivative of both sides. The derivative of x in this case is 1. Over here, what I've got is I've got a composition of functions. I've got f of u, where u equals y. And so I've got the derivative f prime of y times dy dx. And so it makes it very easy for us to solve dy dx as a function of y. So what I've got here is 1 over f prime of y. And this reciprocal nature of the derivative is one of the reasons that we use this f inverse notation as writing as f to the negative 1 power. There's a lot of other reasons for that, which we'll get into later in the course. But what we have here is that if I want to evaluate the derivative at a particular function, I need to take a look at the reciprocal of the derivative of my function evaluated at my particular y point. And so it's this dual technique, the idea that we're using the implicit differentiation along with the chain rule, that's going to allow us to figure out what the derivative of several inverse functions are. And this is going to help build up our library of functions that we can take derivatives of. So the first of these functions we're going to be talking about is sine inverse of x. So remember that we're using this capital letter to denote the function sine inverse x, as opposed to y equals little sine inverse x. This little sine inverse x is the relation that starts at the origin and snakes through to positive infinity and negative infinity in the y direction. Remember that when we're talking about the big letter s, or when we're talking about the arcsine of x, we're only talking about this range that goes from positive pi over 2 to negative pi over 2, where the vertical line test would be satisfied. In other words, when we're actually dealing with a function. So I've got y equals sine inverse x, and my first step is to eliminate this inverse function. In other words, I'm going to take the sine of both sides. So I'm taking the sine of sine inverse x, which gives me that the sine of y is equal to x. And of course, this is the first step to try and eliminate this inverse function. And now what I'm going to do is I'm going to take the derivative implicitly. Remember, the derivative of sine of stuff is going to be cosine of u times dy dx. So I've got the cosine of y times dy dx. On the right side, the derivative of x is just 1. So I find out that dy dx is 1 over cosine of y. And this is what we expected from the notation that we talked about on the previous slide, that it's going to be 1 over the derivative of my original function evaluated at y. The issue, though, is that I started off with a function, and we intentionally restrict our domain and range so that we have a function. But leaving it in terms of y kind of implies that all we have here is a relation. I really want to talk about this in the context of a function. And so what I need to do is I need to go to our trig identities that we learned. One of the trig identities was the sine squared of theta plus the cosine squared of theta equals 1. And so what I can do is I know that sine squared of y plus cosine squared of y equals 1. And I can solve for the cosine of y by subtracting sine squared from both sides. and then of course taking the square root. Now, normally when I'm taking the square root in this situation, I would restrict myself to, I've got a positive and negative square root. However, the thing is, for the angles that we're considering, from negative pi over 2 to pi over 2, cosine is strictly positive. In other words, I'm not going to have to worry about this negative sign. So for our purposes, I can say that the cosine of y is really the positive square root of 1 minus sine squared y. And of course, what was sine of y equal to? It was equal to x. So what I've got here is I've got cosine of y is the principal root of 1 minus x squared. And so when I rewrite this as dy dx equals 1 over the principal root of 1 minus x squared, I now have a function for dy dx, whereas previously I only had a relation. So the first derivative we have is that if I want to take the derivative of a sine inverse function, I'm going to end up with 1 over radical 1 minus x squared. This is the first of our 3 trigonometric functions we'll be talking about today. The next function that I want to talk about is tangent inverse. And I'm going to follow the exact same process in trying to find this derivative. So I'm going to take the tangent of both sides. So I'm going to take the tangent of tan inverse x. And again, remember, I'm restricting this to the function tan inverse and not the relation using the lowercase t. And you may also see this written as the arctangent of x. So when I do this, I get the tangent of y equals x. And I'm going to take the derivative of both sides using implicit differentiation. The derivative of tangent is secant squared of y times dy dx. Anytime I take the derivative of a term involving y, I'm going to get that dy dx equals 1. And so what I've got is dy dx equals 1 divided by secant squared y. And I know there's a great impulse to try and change this over to write this as cosine squared y, but the secant squared is actually going to be more helpful for me. Just as before, I want to think of how tangent and secant are related using trigonometric identities. And I know that 1 plus the tangent squared of theta equals the secant squared of theta. And so for our purposes, 1 plus the tangent squared of y equals the secant squared of y. And so everywhere I have secant squared y, I could replace it with 1 plus tangent squared y. But just as before, tangent of y has a very special meaning. It's x. And so that means that secant squared of y is really 1 plus x squared. And so this dy dx, my derivative, is really 1 over 1 plus x squared. And so what I've done here is I've been able to take the derivative of a trig inverse function, in this case tangent inverse. And one of the things that we recall when we were talking about the tangent function is that our slope is always positive. Turns out that when I do this inverse and I reflect across the line y equals x, this line is always going to have a positive slope as well. Remember, the graph of our tangent function, our tan inverse function, I should say, goes from negative pi over 2 to pi over 2, and I always have a positive slope. Maybe it's negligibly positive as I get towards the negative infinity or positive infinity due to the asymptotic nature of tangent, but positive nevertheless, slightly positive. So our second definition that we have is that the derivative of the tan inverse function is going to be 1 over 1 plus x squared. So we've done the relationship for sine inverse, we've done the relationship for tangent inverse, so the last one of these functions we're going to be talking about is the secant inverse, and we'll discuss the cofunctions in just a moment. But again, as I've done before, I'm going to write this by taking the secant of both sides. This is going to give me the secant of my arcsecant function x, or that the secant of y is equal to x. And I'm going to take the derivative implicitly just as we did before. So the derivative of secant of theta is really secant of theta times the tangent of theta times, in this case, dy dx, because I'm taking the derivative of a y term. And this is equal to 1. So I've got dy dx, which is really equal to 1 over the secant of y times the tangent of y. And I know that the secant of y is going to be x, but just as before, I want to think of what tangent of y is in terms of x. And I'm going to go to that same trig identity we just talked about, the 1 plus the tangent squared theta equals the secant squared of theta. And from this, I've got 1 plus the tangent squared of y equals the secant squared of y, or that the tangent squared of y is equal to secant squared of y minus 1. And so I've got tangent of y is equal to the positive or negative root of secant squared y minus 1, which is really the positive or negative square root of x squared minus 1. But I want to talk about this for a bit. See, I know the graph for secant inverse. Secant is 1 over cosine. So the graph for secant inverse is going to have that same idea where I'm going to be dealing with it being positive in the first and second quadrants. I mean, in the first and fourth quadrants. But what happens is, in my first quadrant angle, I go from 1 to infinity at pi over 2, because that's my asymptote. But from pi over 2 to pi, what I notice is that even though my values for x are negative, my slope is always positive. And from the graph, I notice that my slope is always going to be positive, so I really don't need to consider this expression. The problem is, if I just go ahead and write this as 1 over x times the square root of x squared minus 1, x could be negative. As a matter of fact, x is negative for second quadrant angles. And so I need to compensate for that because my slope is always going to be positive. And one of the ways that we do that is we put these absolute value bars around x. Remember, the reason we're doing this is because empirically, graphically, we know that our slope should be positive for the domain of the secant inverse function. And in order to ensure that, we need to take the absolute value as part of our derivative function. So we have that the derivative of secant inverse of x is equal to the reciprocal of the absolute value of x times radical x squared minus 1. So what we've got here is we've got a derivative for sine inverse, we've got a derivative for tangent inverse, and we've got a derivative for secant inverse. But this, of course, raises the question, what about our cofunctions? Well, the thing is, remember that sine and cosine are related to each other. The thing is, I know that if I'm dealing with a particular angle, I know that sine squared plus cosine squared of that angle has to be equal to 1. But I also know that if theta is equal to sine inverse, then if I'm doing the cosine of that same function, that's really pi over 2 minus x. That's one of the properties that we learned, one of the trig identities in order to convert between sine and cosine. And so what I've got here is that pi over 2 is really going to kind of reflect this across. As we spoke about the cofunctions earlier in this chapter, we noticed that cosine, cotangent, and cosecant all had negative slopes. And so what happens is if I want to take the derivative of my cofunctions, the derivative of cosine inverse, the derivative of cotangent inverse, the derivative of cosecant inverse, if I want to take the derivatives of these functions, I'm going to end up with the negative of their cofunction. So the derivative of cosine was 1 over radical 1 minus x squared. The derivative of cosine inverse is going to be negative 1 over radical 1 minus x squared. And the derivative of tan inverse was 1 over 1 plus x squared. So the derivative of cotangent inverse is going to be negative 1 over 1 plus x squared. And the derivative of secant inverse was 1 over the absolute value of x times radical x squared minus 1. So the derivative of cosecant inverse would be negative 1 over that same expression. And so this allows me to determine the inverse functions of co-functions, the inverse functions of cosine, of cotangent, and cosecant. They're just going to be the opposite of our conventional sine inverse, tangent inverse, and secant inverse derivatives. Because we've noticed that the graphs of cosine, cotangent, and cosecant are negative. They're decreasing, so the slopes need to be negative, the derivatives need to be negative, and we compensate for that with a negative here. So I want to go through a couple of examples of taking derivatives of trig inverse functions. So the first one that I've got here is I've got y equals the sine inverse of 3x squared. And I know that the derivative of y equals sine of u, where u equals 3x squared, I need to do this using the chain formula, the chain rule. And so the derivative of sine inverse is going to be 1 over the radical 1 minus u squared times the derivative of u, which in this case would be 6x. So I'm going to have y prime equals 1 over the radical 1 minus 3x squared squared times 6x, or 6x over radical 1 minus 9x to the fourth. And so this is my derivative for this particular trig inverse function. I want to do one more example, again incorporating this chain rule. So let's say we have that y equals the tan inverse of radical x. So here I've got y equals tan inverse of u, where u equals radical x, which is really x to the 1/2 power. And so I know that if y equals tan inverse, then the derivative is going to be 1 over 1 plus u squared. And the derivative of u, in this case, would be 1/2 x to the negative 1/2 power. So I'm going to be multiplying those two expressions together. So I've got 1 over 1 plus radical x squared times 1 over 2 radical x. That's what it really means to raise x to the negative 1/2 power. And so I've got 1 over 2 radical x times 1 plus x. So this ends up being the derivative of my trig inverse function. So again, there's 3 trig inverse functions that we need to know: the sine inverse, tangent inverse, and secant inverse derivatives. And once we know those 3, we can use the properties of cofunctions to find the derivatives of cosine inverse, cotangent inverse, and cosecant inverse. It's just going to be the opposite of sine inverse, tan inverse, and secant inverse, respectively. In our next lesson, we'll do more examples of more unconventional inverse functions. In other words, how do we deal with inverse functions from a tabular standpoint or from a graphical standpoint? Because those are the types of questions we'll also see on the AP exam. So once again, this is Mr. Potter. Thank you for watching. Have a great day.